Beneath its swirling clouds, Venus is a world of relentless heat, crushing pressure, and volcanic plains stretching for hundreds of kilometers. A planet reshaped by cataclysmic eruptions and alien geology. Aside from a few haunting, grainy photos from the surface, Venus kept its secrets hidden for centuries. No one had truly seen what lay beneath the veil, until Magellan. On the 4th of May 1989, Space Shuttle Atlantis launched its third flight from the Kennedy Space Center. On board, it carried a very special payload, the first deep space probe launched by a space shuttle, a probe bound for Venus that was about to make history. For 4 years, the Magellan spacecraft ambitiously studied our nearest neighbor, mapping 98% of its surface to a resolution of up to 100 m. The images it sent back shattered our assumptions of Venus forever, and that's what I'm going to show you today. I'm Alex McColgan, and you're watching our channel Insane of Curiosity. Join me today as we explore the stunning images of Venus NASA's Magellan mission sent back, the surprises they revealed about Venus's violent past, and the mysteries that still linger unanswered to this day. Mariner 10 snapped some of the first pictures of Venus in 1974, capturing Venus's dense cloud formations on its way to Mercury. A year later, the Soviet Union's Venera program landed a spacecraft on the rocky planet, sending back the first and only images from Venus's surface. They show a desolate, eerie landscape. But these images only captured data from tiny portions of the planet's surface. The lander's cameras could only see a few meters in any direction and were destroyed within hours by Venus's crushing pressures. In the 1970s, the Pioneer Venus orbiter, also known as Pioneer Venus 1 or Pioneer 12, provided some radar mapping data, but its resolution was low and its images incomplete. Imagine trying to map the Earth but Google Maps didn't let you zoom in further than 75 kilometers. New York City would be 1 pixel. So, pretty hard to make an accurate map. Additionally, Pioneer 12 didn't map the northern and southernmost parts of Venus. That's like a map of Earth with most of the Arctic and Antarctic circles missing. NASA decided they could do better. They wanted to see it all: landforms, tectonics, impact and chemical processes, erosion, and even get to know Venus's interior. So they mounted an ambitious mission to capture the entire surface of the planet in ultra-high detail, along with a gravitational map that would give insights into what lies beneath. That mission was Magellan. Now, before I show you Magellan's photos, you need to understand 3 key engineering innovations that made Magellan's mission so groundbreaking. First, to penetrate Venus's dense atmosphere, Magellan improved on Pioneer's basic radar altimetry. Engineers used a 3.7 m high-gain Voyager antenna and components from other past missions to create a synthetic aperture radar (SAR) that collected multiple readings of each area from different orbital positions. These combined readings simulated observations from a much larger antenna, revealing unprecedented surface details. Second, Magellan followed a polar orbital path, scanning Venus in north-south strips during each of its 3-hour 15-minute orbits. In total, it completed 6 243-day mapping cycles. Cycles 1 to 3 mapped the planet's surface and cycles 4 to 6 captured gravitational field data. By the end of its first cycle on May 15, 1991, Magellan exceeded its 70% mapping goal, covering 83.7%. By the end of Cycle 3, it had mapped 98% of Venus at 100 to 250 meter resolution. The probe ended up sending home more data than all of NASA's previous planetary missions combined, a total of 150 gigabytes. By today's standards, it admittedly isn't that impressive. Your phone probably has more storage capacity. But for the early 90s, it was quite something. Finally, after its third mapping cycle in September 1992, Magellan transmitted a continuous radio signal to NASA's Deep Space Network. Based on how the probe's acceleration changed as it orbited the planet, this would produce a change to the radio signal via the Doppler effect, allowing scientists to decipher Venus's gravity field. This revealed information about the planet's interior structure and density distribution. The images I'm about to show you are 10 times sharper than any previous radar images taken from Earth or orbiting spacecraft at the time, and 250 times sharper than Pioneer 12's data. For the first time, we actually got to see what was lurking under those thick, noxious clouds. Let's take a look. Where previous missions had shown only vague outlines, Magellan revealed a world in exquisite detail, revealing for the first time the surface characteristics of our next-door neighbor. This mosaic took a decade to put together, with the bulk of the radar data coming from Magellan's readings. Let's zoom in even further and take a little tour. When you approach Venus, you immediately notice the lack of craters. Compared with the Moon or Mars, it's pretty untouched, with Magellan only identifying 940 impact craters across the entire planet. Many small impact craters are missing because their meteors burn up in Venus's atmosphere. And the other craters we did find didn't look as expected. Take these 3 craters for example, How, Danilova, and Aglaonus. On impact, debris from the surface is ejected and forms the pale yellow blanket-like formations around each crater. Crater ejecta leave behind distinctive marks and shapes that help scientists determine the angle and energy of impact and how long ago it happened, the composition of surface and subsurface materials, and much more. What's interesting about these crater ejecta is they all show sinuous flows in a flower-shaped pattern, not unlike lava flows. They're made of molten rock and remain this way for way longer than expected due to Venus's high surface temperatures. The Adivar crater is another great example of Venus's unique ejecta patterns. On airless worlds like the Moon, ejected material from the impact follows an arced, ballistic path. But on Venus, the ejected debris interacts with the planet's dense atmosphere, creating powerful winds that sweep the material outward in ground-hugging flows. This creates unusual streaks like the horseshoe-shaped one we see here, which are only found on Venus. Finally, the 90 km wide Adams crater has a 600 km outflow tail, likely made of impact melt or magma, which can remain in its liquid form for much longer due to the high temperature and pressure on Venus. The scarcity of these craters suggests Venus's surface is actually quite young. Indeed, gravity data collected by Magellan supports the hypothesis that Venus underwent a global resurfacing event approximately 300 to 500 million years ago. So what could have caused such a dramatic event? Volcanoes, lots and lots of volcanoes. We knew Venus had volcanic features before Magellan, but we had no idea that a staggering 85% of the planet is covered in volcanic flows. Like these pancake domes, 65 kilometers wide, with broad, flat tops less than 1 kilometer tall. They likely formed from highly viscous lava, which later cooled and withdrew, leading to the cracks and pits you can see in the image. Or these sprawling lava flows, stretching for hundreds of kilometers over the fractured plains beneath 2 large shield volcanoes, Sapas Mons and Mat Mons. By studying the varying shapes and patterns of these volcanic plains, scientists can identify different volcanic formation processes, from localized shield volcano eruptions to massive regional lava flooding events. Speaking of Mat Mons, let's take a closer look. Towering at a dizzying 8,000 m tall, it's almost as large as Mt. Everest. It's also a shield volcano, characterized by its broad, gently sloping sides. They're typically formed by fluid lava flows, like the Mauna Loa in Hawaii. If you think Mat Mons looks as awesome as I do, and you want to carry around a bit of Venus fire to spice up your day, then you should check out the wallpapers we have made over on Patreon for your phone, desktop, or tablet. We also have some really stylish posters over on Displate of Venus and the other planets too. Check them out with this QR code or find the links in the description below. Now back to the volcanoes. Shield volcanoes are not the only kind of volcano you'll see on Venus. Small volcanic domes like these are also very common features on the planet's surface. Unlike shield volcanoes, volcanic domes are formed by small, bulbous masses of lava too thick to flow very far. As it slowly exits the vent, the lava piles up and cools on the sides. This cluster of volcanoes sits between rough lava flows in the east and smooth lava flows in the west, indicating 2 different types of lava overlapping, though the exact process remains unknown. The abundance of lava flows and volcanic features on Venus confirm that volcanism played a dominant role in shaping Venus's surface, and gave rise to the theory that the planet might still be volcanically active to this day. In 2024, researchers who were revisiting Magellan's archival data found that 2 volcanoes actually erupted during the probe's watch in the early 1990s. This supported a historic finding from the previous year that Magellan had also erupted in 1991. So what's going on beneath the surface? What is Venus's mantle like? A hint to those answers lies in the surface coronae, like this 500 km wide Yavin corona. When hot, upwelling magma from the depths of a planet's mantle reaches the surface, or the lithosphere, it leaves its mark. On Earth, our tectonic plates shift over this magma hotspot, creating volcanic chains like Hawaii or flood basalts. But Venus only has one single tectonic plate, so mantle plume activity pushes the surface upward before collapsing as the magma cools. The result? These coronae. Despite being hundreds of millions of years old, many coronae appear well preserved. There are around 500 of them, widely distributed across the planet in patterns inconsistent with plate boundaries, and their characteristics suggest a lithosphere that is too thick or strong to break into mobile plates like Earth's. All this evidence suggests a unique style of lithospheric deformation where the crust stays largely in place but is pushed, pulled, and deformed by forces below. This stagnant lid planet model might also play a role in Venus's runaway greenhouse effect. On Earth, our tectonic plates carry out vital processes like burying oceanic carbon. When it rains, atmospheric carbon interacts with mountain rocks to create new minerals which slowly make their way to the oceans and eventually find themselves stored in seabed sediment. This sediment is then subducted when an oceanic plate sinks the seabed back into Earth's magma layer, a process that regulates Earth's temperatures and the concentration of carbon dioxide in our atmosphere. Since Venus's crust is stagnant and devoid of tectonic activity, this regulatory process can't take place. Instead, heat builds up beneath the surface and greenhouse gases are not effectively removed from the atmosphere. The hotter the interior becomes, the more unstable the system, until the whole lithosphere overturns in a global resurfacing event, and the cycle begins again. We aren't exactly sure when the last resurfacing event occurred on Venus, but NASA's technical report following Magellan suggests that it happened around 300 million years ago. Another curious symptom of Venus's unique tectonics and mantle activity are the tesserae that we can see in the highland regions of the planet. They are distinctive geological features characterized by highly deformed terrain with a tile-like appearance. They cover about 8% of Venus's surface and are primarily found in the highland regions. As some of the oldest visible surface features on Venus, they date back about 750 million years. The USSR's Venera 15 and 16 missions first identified these formations in the 80s, but Magellan brought them to life in spectacular detail, like this photo of Alpha Regio, one of the most prominent tesserae on Venus. Scientists still aren't sure exactly how tesserae form, but the two leading theories indicate they are likely made of volcanic rocks, or they are part of Venus's continental crust, deformed through compression or expansion. If so, they'd be gateways into Venus's geological past, and possibly even show us what the climate was like billions of years ago. Fascinatingly, Magellan actually managed to capture the first evidence of active tectonics occurring on another planet in the solar system, in Venus's Aphrodite Terra, a continental area roughly the size of Africa. The image on the left was taken in late November of 1990 during Magellan's first trip around Venus. The image on the right was taken 8 months later, as the spacecraft flew over the region for the second time. See the bright, flow-like area that appeared? It's likely the result of a landslide, which was possibly triggered by a Venus quake. On the 13th of October 1994, after completing one of the most successful deep space missions ever, the probe made its final descent into the atmosphere of the planet it had studied so devoutly over the last 4 years. As it plunged toward the surface, it continued to transmit data about Venus's upper atmosphere until it was consumed by the intense heat and pressure. Over 30 years later, Magellan is still our primary source of information on Venus. And as any good mission, it raised as many questions as it answered. Was there ever water on Venus? If there was, would Venus have been habitable? How has the planet evolved through time? Is Venus still volcanically active today? Together, NASA's upcoming Veritas and Da Vinci missions will set out to answer them and many more. Set to launch in 2028 to 2030, they will revolutionize our understanding of Venus once again. DaVinci Plus will study Venus clouds during 2 gravity-assist flybys, and also send a descent probe deep into Venus' atmosphere to get a better understanding of its gases, chemistry, and water history. Even though it isn't expected to survive the landing, the probe will collect valuable data and images on its hour-long descent to the planet's scorched surface. Meanwhile, the Veritas spacecraft will be a Venus orbiter, similar to Maven currently orbiting Mars. Over the 3 Earth years it spends circling our neighbor, its job will be to search for evidence of ongoing volcanism and tectonic activity by measuring heat coming from the surface and analyzing the composition of Venus's tesserae. These findings will help us understand just how different or similar Venus and Earth are. Could our neighbor really be a window into our future, or is it more like our hot, evil twin? If you enjoyed exploring Venus, you might want to check out my other video on the latest images of Jupiter and Io. Until next time, thanks for watching our channel Insane of Curiosity.